So heat and temperature are related, and yet they are distinct from each other. Heat is the flow of energy from a higher temperature to a lower temperature. We know that if you stick a cold ice cube in a cup of warm water, that energy will go from the warm water to the ice cube. The warm water will cool down, the ice cube will warm up, and eventually they'll get to the same temperature. So heat is that flow of energy from high temperature to low temperature. Heat measures the total energy of a system. Temperature measures the average energy of particles in a system. And so they're very similar and they're very easily confused, but they're not exactly the same. We measure temperature in degrees Celsius, Fahrenheit, or kelvins. We measure heat in terms of joules or calories. In chemistry, there are other units as well. So here we have a picture of two beakers. Both of these beakers have the same temperature, about 100 degrees Celsius. But the beaker on the right has twice as much heat because there's twice as much water. So think about this. Which one of those is going to hurt more if you spill it on your leg? The larger quantity of water or the smaller quantity? The smaller. If you get a drop of boiling water on your skin, it's ouch, right? If you pour a pot of boiling water on your skin, you're going to be in the hospital for a while, right? What's the difference? They're the same temperature. The larger quantity has a lot more energy. Okay, so that's an illustration of the difference between heat and temperature. So units of energy, and since heat is a measure of energy, we use energy units. The SI unit is the joule, and so it's pronounced like jewel, right? Like a jewel in your crown. It's named after an English scientist, James Joule. It's also, electricity is also a form of energy, and that's usually measured in kilowatt hours. And so that's what you'll see from your electric company. But that's measuring the same concept, the same thing, energy, as the joule. The abbreviation for joule is a capital J. The other common unit is the calorie, and this is abbreviated CAL, that's not California, lowercase c. And we are familiar with calories, right? Because people are always talking about how many calories are in this and that and the other thing. Calorie is a unit of energy. Your food provides your body with energy, and so the calories are the measure of how much energy is in the food. But this is a calorie with a lowercase c, and the calorie you're talking about in terms of, oh, the candy bar is 260 calories, that's a big C calorie, a nutritional calorie. Okay, so a big C, and the big C is carried along in its abbreviation, is equivalent to 1,000 of those little C calories. So essentially, a nutritional calorie is a kilocalorie. Kilo means 1,000. And so 1 kilocalorie is 1,000 small calories, and that's what a nutritional calorie is. Well, what is a calorie? A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is approximately equal to 4.184 joules. So we see that a calorie is a larger unit than the joule. And we're kind of 50-50 in chemistry. We use calories and joules, so we need to be comfortable with both of them. Specific heat is related to this, but the specific heat of a substance is the amount of heat needed to bring about a change in temperature. This is expressed in units of calories or joules per gram per degree Celsius. So calories, how many calories for each gram and for each degree Celsius? Because if you have more substance, it's going to take more energy to change the temperature. So more grams, you're going to need more energy. If you want a larger temperature change, if you're starting with ice on your stove and you're trying to bring it to boil, to make spaghetti or something, you're going to have to put a lot more heat into it than if you start with hot water from the tap. So the amount of energy to change the substance temperature depends on how much of it you have and the difference in temperature. So the larger the specific heat, the more heat is required. Some substances heat up much easier than other substances do. And when we look at the specific heat, we can see that quantified. So here we have specific heats for different substances. Here are solids. Here's aluminum, 0.215, graphite, diamond. Here's copper, 0.092, silver and gold. Now, in cookware, pots and pans, do you want the pot to heat up quickly? Yeah, because you need it to transfer heat to the food inside. So that's why you see a lot of cookware that has copper bottom, because copper has a very low specific heat. It heats up quickly. Iron is pretty good as well. Aluminum is often used, but it takes more energy to heat it up. But aluminum doesn't corrode like copper and iron do. If we look at liquids, and these are all in calories per gram degree Celsius, we see that water has a much higher specific heat than these other liquids do. And here are different gases, and these are also lower than water. Water has a very high specific heat. Water plays a big part in moderating temperature. That's why when you go to the coast, the daily temperature fluctuation there might be only like 10 degrees from the high to the low, because you have this ocean that acts as a heat sink, and it gives off heat at night when the sun's gone and it's cooling down, and it absorbs heat during the day and keeps the temperature from going too high. Around here we can have a 40-degree fluctuation, no problem. It can be 60 at night and 100 in the afternoon because it's dry and we don't have the water to absorb heat. Well, we quantify temperature changes with a relationship like this. We can calculate the amount of heat that's needed to heat a mass by a specific temperature change. And so this is an important equation, and you're going to see a worksheet on this in activity session today. Just written a little shorter, it's Q equals MC delta T. It might help you. That almost looks like an A, right? So Q equals MCAT. That's a test you have to take if you want to go into medicine. So it kind of looks like Q equals MCAT. You need to know this guy. Mass, the specific heat capacity, and the change in temperature. This triangle is the Greek letter delta, the capital delta, and that means change in. And scientists use that for all kinds of things. And when we talk about delta, the change in temperature, we always mean the final minus the initial. So delta T, didn't mean to have that in red, but oh well, is going to be the final minus the initial. Because you can have a positive temperature change and you can have a negative temperature change. A negative temperature change means that the temperature went down. And a positive temperature change means that the temperature went up. So we can do more calculations. There's no cheering. Aren't you excited about more calculations? I'm just kidding. I know you're not excited. That's fine. I didn't expect you to be. Just, hope springs eternal. Okay. Calculate the calories of heat released when 7.4 grams of water cools from 49 degrees Celsius to 29 degrees Celsius. And here's C for water, 1.00 calories per gram degrees Celsius. You do not ever need to memorize the specific heats. They will be given to you in a problem or you can look them up in the table. So we've got numbers here. Let's write down the numbers. 7.40 grams, 49 degrees Celsius, and 29 degrees Celsius. And we're trying to find calories of heat. So hopefully the equation that we just learned will come to mind. Q equals mc delta T. And what are these numbers? 7.40 grams. Which of those letters is that? M. It's the mass. And these guys are both temperatures. Which one is the initial temperature? 49. It says it cools from 49 to 29. So this is the initial temperature, and this is the final temperature. Can we calculate the change in temperature then? Yeah. Delta T equals the final temperature, TF, minus TI. So the final temperature is 29 degrees Celsius. The initial temperature is 49 degrees Celsius. And that gives us minus 20 degrees Celsius. But this is a significant figure because we've got two numbers here, temperatures that we're subtracting, and they're each to the nearest 1 degree, and so this answer is to the nearest 1 degree. We're going to keep track of that. We have a negative temperature change. That's okay. The temperature went down. Down is negative. So we're trying to find Q. We've got M. We just calculated delta T, and they gave us C. So we're just going to put them into this equation. Q equals the mass, 7.40 grams, times the specific heat capacity, 1.00 calories. Make this a vertical fraction, grams, degrees Celsius in the bottom, times the change in temperature, and then do that on your calculator, 7.4 times 1 times negative 20. And the calculator says minus 148. And let's look at what happens with those units. The grams are going to cancel out. And the degrees Celsius are going to cancel out. And we're left with a unit of calorie. See that? Then we have to look at sig figs. How many significant figures in 7.40? 3. Trailing 0 with a decimal point, we count that one. How about 1.00? 3. These are not exact numbers. These are measured quantities. And minus 20, how many? It's got 2. Remember, we looked at the result of this, and I put that decimal point there because that is a significant digit. So this is 2. So then this should have 2 significant figures. So you could say this is minus 150 calories, or a better answer would be minus 1.5 times 10 to the 2 calories. Now, we haven't run into negative numbers before. Heat is something that is going from something to another thing. And so whether it's positive or negative depends on your point of view. If you think about money, okay, if I pay you $5, that's positive for you and negative for me, right? So the same transaction can be described as positive or negative depending on whose point of view you're taking. In these energy calculations, we're taking the point of view of the substance that's changing temperature. Here it's the water. The water is cooling down. If it's cooling down, is heat coming into it or going out of it? It has to be going out. Heat leaving is just like money leaving my wallet. To me, it's negative. Yes?
The word problem it asks for release. So basically, you're just saying that it gained 150 calories with the grams.
That's a very good point. The question is saying, calculate the heat released. And different books, and I'm not sure what Mastering Chemistry does in this book either, some courses kind of gloss over the whole negative thing. So heat released, the released tells us the direction. And so then you would say 150 calories were released. If you're just calculating Q, you would say Q is negative. I want you to pay attention to the negatives in these equations, because when you get to 1A, they're going to care about it. Okay? And I want you to understand what the negative means. This means that the heat was leaving the water. So yes, the best answer to this, how many calories were released? 150. Yeah, because if you said negative 150, then that would be implying that negative 150 is released, which means that 150 was gained. That was your point, right?
Correct. So the correct answer would be Q equals negative 150 calories?
I wouldn't say Q equals. I think the best answer would be 150 calories were released. They're asking the question with words, and then we should answer with words. If you're answering with letters and numbers, then we should keep the negative sign.
So if we come across something like the second question, that's when we actually get the specific numbers, and that's a specific thing.
Right. Some of them are going to, if this one said calculate Q when 7.40 grams, then we would just say Q equals minus 150. And it is a bit confusing, and I'm sorry. I wish I could avoid it, but it's just there. So we'll just have to face it and go on. Okay, so let's do the second one, because this one's a little different. Find the specific heat of silver in joules per gram degree Celsius if 38.5 calories is required to heat 25 grams of silver from 31.5 to 58.7 degrees Celsius. So again, let's take these numbers and write them down. 38.5 calories, 25.0 grams, 31.5 degrees Celsius, 58.7 degrees Celsius. And then we identify them. The units help us. Calories. Is that Q, MC, or delta T? That's going to be Q. Q is heat. Calorie is a unit of heat. Here we've got gram. Well, that must be the mass, right? And then we've got two temperatures. And so we need to look here from 31 to 58. So 31 is the initial, and 58 is the final. Let's go ahead and calculate delta T. It just makes the rearranging of the equation simpler. So final minus initial. Here the final is higher, 58.7 minus 31.5. It also makes the whole significant figures thing easier because you actually wrote down the step. Minus 31.5. So my calculator is showing me 27.2 degrees Celsius. And let's just evaluate sig figs for that intermediate result. Subtracting, we're looking at what place the uncertainty is in. Here it's in the 10th place in both, and so the uncertainty there lies in the 10th place. This number has 3 sig figs, and so that's what we'll consider in the rest of this. So the equation we use is Q equals MC delta T. But this time we're not calculating Q, are we? We're calculating C. So I'm going to make that green. Rearrange the equation first, and then plug numbers in. So what I want to do to get rid of C, to get C by itself, is I need to make the other things with it go away. It's like M, I need you to bug off. Delta T, go away. The way we do that is we do the opposite. So here it's M times C. That means we're going to divide by m. So I'm going to divide, let's just use a different color here. I'm going to divide by m. If I do something to one side, I have to do the same thing to the other side. It's like dealing with twins. If you give one twin a cookie, you have to give the other twin a cookie, right? Or you're going to hear about it. So if we divide one side by m, we have to do the same thing over here. What's m divided by m? It's 1. Those cancel out. Yay, we got rid of m. We're going to get rid of delta t in the same way. If we divide by delta t over there, we have to do it over here. And the delta t's cancel out. Okay, if you have algebra issues, please get some help. Talk to Josh and ETC. Come and talk to me. I can help you, okay? I've taught algebra to a lot of people. Yes?
Couldn't you just divide the whole thing by m delta t and then just do that in one step?
Yes. I'm just trying to show the thought process for people who have struggles with rearranging equations, which I'm assuming is probably about half the class. Yeah, if you're good with rearranging things, you can look at the equation and just write down what it rearranges to, and that's awesome. But not everybody can do it. So that looks like a big old mess now, so let's rewrite it so we can see it clearly. So C is going to be equal to Q divided by M times delta T. We have those things already identified. We're going to plug them into the equation. Always put the units in your equation. Down here we've got the mass, can't read, 25.0 grams, and delta T, 27.2 degrees Celsius. Be careful when you're dividing, you've got two numbers in the denominator. There's bad things that can happen on your calculator. This is how I do it. I do 38.5 divided by 25 and divided by 27.2. That's what I recommend. 0.056617 647.
You don't have to add a negative?
No. And what's the unit going to be? All of these, right? There's not really space there. I'm going to round this off real quick. How many sig figs should I have? 3. This guy had 3, and that's 3 and 3. So 0.0566 calories per gram degrees Celsius. Yes?
It says joules per gram.
Yes, it does. It does. So then we're not really done.
Yeah.
But we're in the right track. Thank you for pointing that out. Just back to this guy. No, this guy. So if you say, why are you dividing? That's multiplying. Okay, you can do it that way. Follow along with this. You would do 38.5 divided by, and you're going to have to use parentheses if you really want to multiply. So you open the parentheses, and then you do 25.0 times 27.2, close the parentheses, and then press equal, and you'll get the same number. Make sure that you can communicate with your calculator and come up with the same answer. Now, as Josh so wisely pointed out, that is not answering the question that we need to answer, is it? Because it asked for joules, and we calculated in calories. Horrors. Do we have to do it all over again? No, we just need to convert. So I'm going to bring it up here where I made some space. 0.0566 calories per gram degrees Celsius. And I'm just going to use a unit factor. I want to multiply by joules and divide by calories so that I can get rid of calories and replace them with joules. Dimensional analysis tossed in at the end. 1 calorie is 4.184 joules. I'm not going to make you memorize that, but if you do enough problems, you might remember it. I'll give it to you on an exam. Okay, so I'm going to take that 0.0566. I still have this number in my calculator, and so I'm going to use the whole thing, because this really wasn't our final answer. We shouldn't have rounded it just yet. So I'm going to multiply by 4.184 and press the equal sign. And I'm going to get another big horrendous number. Joules per gram degree Celsius. And this should still be rounded to 3. So my final answer is 2.37 joules per gram degree Celsius. Any questions? A problem like this can be difficult not because the individual steps are difficult, but because you may forget where you're going. Okay? And so sometimes if you struggle with word problems, you might actually just want to write down a plan of attack. Okay, I'm going to identify all my numbers. What do they mean? I'm going to rearrange the equation. I'm going to check my units. I'm going to convert my units so that you can go back and refer to that. Yes?
Even though it asks for joules over grams, including the Celsius in the denominator is okay in the answer?
It's asking for, it kind of got obliterated, it's asking for joules per gram degree Celsius.
Oh, okay.
Yeah.
I read that wrong.
Yeah, this is all together.
Oh, okay.
I kind of think there really shouldn't be a space in there, but there is. Good question. Anybody else? We're not going to do that one. We're not going to do that one either. Or that one. My goodness, there's a whole mess of them at the end here.